All right. So, welcome to June. It is now June 1st. So we are in the home stretch, folks. We just have a couple more weeks to go. And what we're going to do today is continue where we left off last time, which was looking at solving oblique triangles, so the non-right triangles. And we saw that we have the law of sines, which helps for many of the different scenarios. We'll do a couple more law of sines just to kind of keep that fresh and show you some of the other issues with that side-side angle one. And then we'll develop another law called the law of cosines that will allow us to take care of the other scenarios, the side, and side angle side. And then once we're done with that, we'll look at calculating areas of triangles, some different ways we can do that as well. So today is going to be a lot of actual trigonometry, actual measurement of triangles. So, but before I dive back in, are there any homework questions, anything out there that people have questions about from the last few classes? All right, well, it looks to me like there are, hold on here. So, William, when you say number 9, can you give me a little more information, please?
Yeah, sorry, I was just trying to get it in before you moved on.
Yeah, no
so yeah, number 9 on the, was it 10.1? Just the, yeah, 10.1 practice.
10.1, okay. Let me go find that and we'll take a look at it. All right, I got that number 8 instead of number 9, not a problem. Darn it. I clicked on the wrong thing. All right, well, let me go ahead and share my screen. We'll get you guys so you can see what this question is. All right, so hopefully you guys can all see my screen. Okay, so here's number 8. So again, yours should look something similar to this, if not the exact numbers. So it says we've got a communication tower located at the top of a steep hill. The angle of inclination to the hill is 57 degrees. A guy wire is to be attached to the top of the tower and to the ground, 125 meters downhill from the base of the tower. The angle formed by the guy wire is 22 degrees. Find the length of the cable required for this wire. Okay, well, I'm going to draw the picture just so that I've got it here with all the different numbers. And this is now going to be an applied problem, which means we're probably going to use the law of sines. Seeing we don't know anything else. So we'll see if we can make this conform to the law of sines. And we want the length of the wire. Okay, so I think I've got all the information, at least from my problem, up on the whiteboard. So I'm going to stop sharing here, and then we're going to go to the whiteboard. All right, so I've got a picture here that's got pretty much what we're looking at. We've got the tower. We've got X is the guide wire that we're trying to calculate its length. And then I've got our various different angles. So clearly we're going to want to use this triangle right here, the one that's made by the tower and the guide wire. So let me just redraw that, because we can maybe make it a little less cluttered. So we've got 125 is this length. We've got the unknown length X. And right now we've got one angle. So we don't have enough information yet to solve this triangle, because remember, for triangles, we need to have three things. So we either need to get another angle or another side. Well, I think trying to get the side lengths pretty much are going to be impossible, because one of them we're looking for, and the other one is the height of the tower, and they didn't tell us anything about that. So the question is, can we maybe figure out some other angle? And the answer to that is yes. We actually can figure out one of the other angles. We just have to be a little bit sneaky and use some geometry. So does anybody see the angle we could actually calculate? So the interior, I don't think I know what you mean there, but opposite of X. Yeah, I definitely like that. Let's look at the one that's opposite of X, and maybe that's what you meant, Adam.
No, I meant to draw parallel lines from the ground to the bottom of where there would be an imaginary 90-degree angle.
This guy right here?
Yeah, no, other way, perpendicular to that.
Okay.
And then that's now technically a right triangle with the now additional angle is a alternate interior angle.
Correct.
Which are a congruent.
Yeah, so this guy, we know that this is also 57 degrees, which we can add to the 90 degrees right there, which gives us a total of 147. So it turns out that this angle right here is 147 degrees. We also could have done it by dropping this perpendicular, because then we know that this angle right here is 33 degrees. We can take that away from 180 to get the 147. Okay, but now we've got enough. We have angle, side, angle, which we saw last time is one of the things we can use the law of sines for. And so if we start using the law of sines, I went ahead and rewrote it just to kind of remind you guys how this works. It's the ratios of sides and the sine of the angle opposite those sides. We know that those ratios are all the same. So in terms of this one, trying to find for X, we need to know the angle that's opposite X, which we now have, right? So we can write X over sine of 147. And now all we need is another side angle pair. So in terms of the sides, since we do have one other side, we need to use that. So we'll put a 125 up here. But then below that, we're going to need the sine of the angle opposite the 125, which is this little one up at the top. So how are you going to get that one? All right, so Era's just said 180 minus ... I like that. Yeah, we know that the total sum of all the angles is 180 degrees. So we can take the 180 minus 147 and minus 22. And I believe that that leaves us 11 degrees. All right, so that guy's 11 degrees. So we go ahead and put that in there, and now we've got enough information to get our x. So I'm going to leave it right here. Obviously, you can use your calculator to get a number, but that will be the length of this guy wire. So sometimes you got to get creative in terms of finding information when it's not given directly. Like this time we had to make use of, well, we did it with alternate interior angles of transsectors over parallel lines, right? But whatever you use, this is where your geometry is going to come in helpful. The more of that you remember, the easier these applications are going to be, because you can pull tricks like that. All right, but is that good, William? Does that make sense? Does that help a bit? Yeah, thumbs up. Okay, cool. All right. Anything else from the homework we want to look at? All right. Well, I want to talk a little bit more about this ambiguous case for the law of sines, because we saw last time, I kind of left you, I dropped a bomb on you as we were just leaving, that when you're in that side-side angle case, it turns out you don't know for sure that you have a right triangle, and in fact, you might have more than one. So let's talk about this again. So the SSA case. So we call this the ambiguous case. And that's because we can have two solutions. So you can actually have two triangles that work, or you can have one solution. So I'll put here only one. But it also turns out you can have no solutions. It is possible that with certain combinations of side-side angle numbers that you don't get a triangle. All right, so I want to talk a little bit about why this is, why you could have two or one or possibly none. And it's very geometric. I mean, I can also show you using the algebra on the law of sines why we have to worry about that, and I will. But in this situation, we really don't know until we try to run the number. So let me show you first why this happens. So I'm going to draw a generic side-side angle situation. Okay, so let's say that this is one of the sides that we know. We also know this angle. And so then the other side would be like up here, right? So we've got side, side, angle. Now, in terms of which of these cases we have, it's totally dependent upon this second side, this side that's opposite A. And it's determined by how long that is. Because like right now, if you were to look at this situation, in order for me to make this a triangle, I basically need to get this side, think about swinging this side, rotating it. We need to rotate it until this point on the end of it, touches this dashed line. And you could see in this situation, let's just say that that S is the length of my pen. No matter where I rotate it, it's never going to actually hit this dashed line. And that would be this situation where we have no solutions. Now, if we were to make it longer, like let's go ahead and lengthen it so that it reaches this point. So there would be a triangle. But I could take that same length and rotate it over here. And notice that it gives me a second triangle, this little thin one, okay, where those two are the same length. And so this is what happens when we run into the having two solutions. These combinations of numbers, the two side lengths and that angle, make it so that it's possible to have this sort of picture. All right. Now, in terms of having only one solution, that happens if we make this long enough so that as we rotate the other way, we can't fill in the circle, or it's just long enough to make it a right triangle. But that's what's going on geometrically in this situation. Now, algebraically, the reason that this happens is that we're solving for an angle, right? Like, just let me throw some numbers here, for example. Let's say we've got A is 22, B is 35, and then I give you alpha as well. So we'll go alpha is equal to, let's say 38 degrees. So we want to get the rest of this information, right? So we want a C, we also want a beta, and we want a gamma. But from the law of sines, the only thing we can do is solve for beta. So think about what law of sines does there. We've got sine of beta over B is equal to sine of alpha over A. And so if I want to solve for beta, I get sine inverse of B sine alpha over A. So whatever those numbers are, I plug them in, and then I take an inverse sine. But now here's why we can run into two solutions, one solution, or no solutions. So the no solutions, that's going to be when this number right here is bigger than 1. If this is bigger than 1, then there's no solution. And that's because inverse sine has a domain of -1 to 1. That's the range of sine. You may remember that sine, the only numbers that come out are between -1 and 1. And so we have the issue that this is bigger than 1. Okay. Now, I should also say, or smaller than -1. Because it's possible that that number ends up being negative, depending upon what alpha is. Alpha would have to be an angle that's greater than 90 degrees for that to happen. Oh, actually, I lied. That'll never happen. Sine is always positive in a triangle. But anyway, the point of this is that we get out of the domain, and so we get no solution. So that's what happens algebraically. That leads us to the no triangle solution. And then the reason that we can get 2 is because inverse sine only returns first quadrant, right? Whatever this beta is, it's going to be forced to be a first quadrant angle. And that's because of the restriction that was put on sine for inverse sine to even exist, right? Inverse sine can only give us angles between -π/2 and π/2. And this will give us something that's in the first quadrant. And the issue is, though, that beta could actually also be a second quadrant angle, something that's bigger than 90 degrees. And if you look at this picture where we found 2, this guy beta that basically we're calculating here on the triangles, that's these 2. And the one on the left is the one that would be a second quadrant angle because it's bigger than 90 degrees, right? What we call obtuse. The one on the right is a first quadrant angle. we'll call that acute. But both of them are possible, and both of them have the same sine value. So that's why we get the sometimes 2. All right, and then the one just works out that whatever angle we get is the only one that is possible. And those are nice situations, but you always have to check. Always have to check the second possible angle. And so just to kind of remind you about that, how you can find the second one. The second one, since it's in the second quadrant with the same reference angle as beta, you actually get it by doing 180 minus. So here are your 2 possibilities. Okay, so if you go and you solve for, like in this case, beta. So I'm going to write here beta 1. That's going to be whatever we had the sine inverse of the stuff. Beta 2 is going to be 180 degrees minus beta 1. So you should always check that. Always look and see, what does beta 2 look like? Is it small enough to fit in the triangle? Basically look for how many degrees are remaining, right? Like look at this case. We've used 38 degrees, like if we're going to run with these numbers. We've already used 38 degrees, which means there's only 142 degrees left. So if we find out that this beta 2 is bigger than 142, we just ignore it and we go, okay, that is not a second solution. So even though you have to pay attention to this one, you have to watch out when you have the side-side angle case, there's a very routine thing to do. You find the angle. Once you find that angle, look for the second angle. See if that second angle fits. And any angles that work, you go ahead and find a triangle using those angles. So let's go through this one. Let's actually take these numbers and let's see what we find for beta, and then we'll check our second beta and see what happens. All right, so we're going to plug in our numbers. So in this case, I'm going to go ahead and just jump down to this. We're going to have that beta is equal to sine inverse of 35 sine of 38 degrees divided by 22. So I'm just taking what we did generically and I'm putting in the specific numbers. And now we can use our calculator. So if you do the inverse sine on this, your calculator should yell at you. And right here, DNE does not exist. If your calculator doesn't yell at you, it's because it's smart enough to know that this angle is an imaginary number, but we're not going to do anything with imaginary numbers, or imaginary angles, I should say. Imaginary angles, they're not useful when we're actually measuring triangles in the real world because real world, right? But, oh, I totally lied. This does too exist. I just ran the numbers on my calculator and I got a number. So let me go ahead and change that. It was a different example I was thinking about. All right, so this gives us beta equals 78 point, let's just round it to 4. All right, so there is an angle that works. So the question is, what about beta 2? So let's look at beta 2. It's going to be 180 minus 78.4, which is going to be 101.6. So it's a real easy just subtract from 180. But the question is, does that fit? Do we actually have two triangles this time? All right, so Kiva just says, yep. And she's right. This one definitely does fit because remember, we used 38 degrees. If I add to it 101.6, there's still plenty left over. So we're actually going to get two different triangles. One that uses 78.4 degrees for beta, and the other one that uses 101.6. So for each of those, there's going to be a gamma. So I'll write them as gamma 1 equals and gamma 2 equals. So again, the way that we find that third angle is to take 180 and subtract these other things. So for the first one, when we take 180 and we subtract off the 38, and then we subtract off the 78.4, that ends up giving us 63.6. And then similarly, for the gamma 2, if we take the 180 minus 101.6 and minus the 38, that's going to give us 40.4. And then once we have those gammas, we can find C. We'll go back to the law of sines. So let me run up to the top here and I'll show you how to find the first one. So if I want C, call it C1, and be C1 over the sine of 63.6 is going to equal 22 over the sine of 38. So I'm doing C over sine gamma, and then I have to attach it to one of the other pairs. I went ahead and went to alpha because, like I told you before, my default is to go to the one that I didn't calculate, because anytime I do a calculation, there's the potential that I make a mistake. So this way I'm guaranteed that that won't be a problem. All right, so you go ahead and solve that for C. So you do 22 times the sine of 63.6 and then divide by the sine of 38. You find out that C1 is equal to 32. My calculator gives me 32.007, so we'll call that good. And then C2, it's actually really easy to get because the only thing you have to do is change this 63.6 to a 40.4. So if you've got a calculator like a TI-89 or something where you type stuff in, you can actually just backtrack and delete. That's pretty easy. But C2 would be 23.16. All right, so again, the ambiguous case. You never really know until you run the numbers and see what you get. So I'd love to give you some great words of advice here, but there are none. Side angle, it's a pain in the ass because you always have to check it. But a great way of remembering that this is the weird situation is just remember that this is ass backwards. No, literally, it's ass backwards, right? If you look at this, we go backwards, ASS. All right, so just remember that the ass backwards is ambiguous. So, if you ever have that side angle, just realize that it is ass backwards, so you got to worry about it. You got to think about it. Okay, well, hopefully that's a good little review of the law of sines and how that works. And just remember that this is good for side angle, or as good as anything can be for side angle. But it's also good for the two cases where you have two angles and a side. All right, so Bella, how I got C2 was exactly the same thing, except instead of 63.6, I used 40.4 because it's a different gamma. It was the gamma for our second case. Okay, good. All right, so this leaves us two more cases. If you remember all the different possibilities that we could have for three pieces of information. The other two that still remain are side, side, side. So I was going to put here. What about side, 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 and side angle side? Now, the problem with both of those, at least in terms of the law of sines, is that neither one of them gives us a side and angle pair to start the proportion, right, to create one of the fractions in the law of sines. Obviously, side, 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 we have no angles. And with side, angle side, the angle is opposite the unknown side and therefore isn't very useful. So what we're going to have to do is create another tool. And this one's called the Law of Cosines. So we're going to go ahead and build it. It's actually pretty easy. We're going to do something kind of like we did last time. Okay, so I'm going to go ahead and drop a perpendicular here, but let's say these are sides A, B, and C. And that perpendicular, I'll just call it H for right now. And I'm going to go ahead and put alpha here. Obviously, beta is on this side, and gamma is the one that we're splitting, but I'm just going to put alpha because that's the only one we need right now. Okay, so here are some things that we know. First things first, though, I am going to split this C so that one of these sides, that's length X. So if that's length X, then the remaining piece is going to be C minus X, right? You tell me how long this is. If I take it away from the whole length, I get the remaining piece. Now, in this picture, you see two right triangles. And in those two right triangles, I can use the Pythagorean theorem. So think about this one on the left. I'm going to get x squared plus h squared is equal to b squared. And then the one on the right, that's going to tell me that h squared plus c minus x squared is equal to a squared. So I've got a lot of extra letters in here. I've got h's, I've got x's, I don't want any of that. So I'm going to start replacing them. Like this first one, if I solve it for h squared, that's equal to b squared minus x squared. So I'm going to take all of that and just fire it in over here. At the same time, I'm going to multiply out the c minus x squared. So we're going to have h squared, so that was now b squared plus x squared, plus c squared minus 2cx plus x squared equals a squared. So all of this, the c squared minus 2xe plus x squared, that comes from FOILing out c minus x squared. Okay, but now notice I've got a minus x squared and a plus x squared. So those things cancel. We can slash those. So this is starting to look pretty good. It's getting rid of almost everything. All I've got left in there is an x. So I've got b squared plus c squared minus 2cx equals a squared. All right, well, here's how we're going to get rid of the x. I'm going to come back to that first triangle, the one that's over here on the left, and think about the trig function that relates x and b. So with alpha, that's the adjacent side over the hypotenuse. So that's cosine. So we've got cosine of alpha equals x over b, which means x is equal to b cosine alpha. So I can put that in for my x. And once I do that, let me just erase this and we'll put what it looks like when it's complete. We're going to have a squared that equals, just moving it to the other side to make it a little bit neater. We're going to get b squared plus c squared minus 2bc times the cosine of alpha. So you can see the 2c here, the b and the cosine alpha came from our x. All right, so let's put a box around that. Because that, my friends, is the law of cosines. So it's called the law of cosines because it involves the cosine of an angle. But notice what this includes. This includes all three sides, A, B, and C, and then in this case, the angle opposite A. So you can see why this is going to work for side, 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 for example. If I tell you the three sides, you know A, B, and C, which means you're going to be able to solve for alpha. Also, if you know two sides and the angle in between them, let's say those two sides are B and C, the angle in between them is alpha, that means you know everything on the right, which means you're going to be able to solve for that third side. Now, when I did this and I drew this perpendicular, I could have drawn the perpendicular from any of the corners, right? Take any of those vertices, drop a perpendicular. I could have done something similar. And so there are actually two other forms for the law of cosines, but they're very similar to this one. The one that starts with b squared, it's going to be a squared plus c squared minus 2ac times the cosine of beta. And then the one that has c, it's c squared equals a squared plus b squared minus 2ab times the cosine of gamma. So in terms of the forms, if you know one of them, it's really easy to get the others. You just swap some letters and call it good. All right, so there you go. There's the law of cosines. Fun fact, you look at this bottom one, it looks a lot like the Pythagorean theorem, right? Or at least it starts out that way. If I could just cover up this piece, you can see the Pythagorean theorem, right? We've got c squared equals a squared plus b squared. Well, the Pythagorean theorem is a specific case of the law of cosines. Think about what happens when your angle is 90 degrees. 90 degrees, pi over 2, same. So what's the cosine of 90 degrees? Well, it's 0. So in a right triangle, this piece goes away, and what you're left with is the Pythagorean theorem. So I could say, you actually already used the law of cosines. You would say, I call bullshit on that. I've never used the law of cosines. But anytime you use the Pythagorean theorem, you were using the law of cosines, just the specific case when that angle is 90 degrees. All right, so let's do a couple examples. Let me show you how this works, because it's not really that tough. It's just a matter of putting things in the correct places. And one other thing I just want to mention, sometimes students ask, do we have to remember how you came this? Are we going to be able to, are we going to have to be able to produce this again? And my answer to that is no. I show you this because I think it's important to know where formulas come from, because then you know it's not just being made up. But in terms of being able to reproduce this, no, I don't expect that. Hopefully you at least see where it comes from, and maybe even some of you find it interesting. I know that's a big hope, but hey, I can always dream. All right, so let's do a couple of examples. Let's do a side, side, side. Let's do a side angle side so you can see how they go. And you'll see it's pretty straightforward. All right, so here's an example. Let's say I give you this information. I'm going to tell you that A is 28, B is 33, and gamma is 26 degrees. So that means the other things we need to figure out are alpha and beta, and then also C. All right, so this is side angle side. We know two sides and the angle that's in between them. So law of sines is off the table. So let's go to the law of cosines. So let's look at what we know and think about which of these we want to use. So in terms of which one you want to use, it's really easy to pick. Just go to the one that has the angle that we know. So we know gamma, so we're going to go to this bottom one. We're going to go to the c squared equals a squared plus b squared minus 2ab cosine gamma. All right, now also in here though, we know A and we know B. So it turns out that we know everything on the right-hand side of this equation. We're going to get that c squared is equal to 28 squared plus 33 squared minus 2 times 28 times 33 times the cosine of 26. And this is beautiful. We can just punch this into our calculator and then take a square root. So once we remember the form and we just put stuff in, it's a super easy calculation. So square these two, add them, subtract all this other stuff, then take that and take its square root, and we get C is equal to 14.56. Well, cool. So now we've got C. All right. So now we got to find alpha and beta. So we could use the law of cosines again. We'd have to use a different form though, right? We'd have to use the form that involves alpha or beta. But we don't have to. We can actually use the law of sines now. And that's what I recommend that we do. Now that we've got a side angle pair, look over here, we got C and gamma. Now that we've got that side angle pair, we can go to the law of sines. I recommend doing that because the law of sines is a little bit easier. Most of us like it a little bit better. So the only question then is, do we find alpha or do we find beta? Well, I'm going to suggest that you find alpha, and I'll explain why in just 1 second. So let's use the sine of alpha over A. That's going to equal the sine of gamma over C. So we've got sine of alpha over 28 is equal to sine of 26 over 14.56. All right. So if we do the inverse sine on this, we get alpha equals 57.45 degrees. But this is probably a really good time for me to go, or, because this isn't our only option. When we use law of sines, remember there's also another possibility. What is the other possibility? All right, so Era's just put, we subtract from 180, and Kiva just said 122, which is pretty close, right? The other option, if we take this away from 180, it would actually be 122.55. Okay, so we have an or. Well, crap. Okay, so here's the deal. There's something else that the law of sines tells us. I didn't mention this before because I wanted to bring it up here. But go back and look at every single triangle we've found. And I want you to notice something about the lengths of the sides and the angles opposite them. What you'll notice is that the smallest angle is always opposite the shortest side. And similarly, the largest angle is always opposite the longest side. Okay, so this is just fact, and I'm going to go ahead and write it up here. Okay, so the smallest angle is opposite the shortest side. And then similarly, the largest angle is always opposite the longest side. And that has to be true for the law of sines to hold. If these fractions always have the same amount, if we make the bottom bigger, so we make a greater length, we need a bigger number from our sine, which means bigger angle, and vice versa. All right, now that we know that, that actually tells us that this alpha, the second choice, isn't possible. If we get an angle bigger than 90 degrees, it's going to be the largest angle. Has to. You can't have two obtuse angles in a triangle. Well, A is not the longest side. We know B is longer. So that means A cannot give us the biggest angle, which means alpha isn't 122.55. So I'm going to cross this off as, even though the sign of alpha suggests that that's a possibility, the triangle itself doesn't. All right, now we can't have two choices here anyway, because this is not an ambiguous case. The only ambiguous case is side-side angle. And this is how we can justify that there is only the one. And so remember when I said, let's start with alpha, and I'll tell you why. This is the why. I went with alpha because I knew it was the smaller of the remaining angles. And if you're searching for a smaller angle, it will never be obtuse. So you never have to worry about the or. Okay, well, I'm going to write one more thing down in just a second that kind of pertains to that, or at least put it down in words so you can see it. But I want to go ahead and finish this real quick. So we found out that alpha is 57.45 degrees, which means in order to find beta, we just have to subtract that 57.45 and 26 from 180, and that gives us the beta is equal to 96.55 degrees. And you can see this fact again, that the smallest angle is opposite the shortest side, and the longest angle, or largest angle, is opposite the longest side. Okay, so even though law of sines is easy, it does come with this big if and this big So let me just give you this fact right here. When using the law of sines, and you have a choice of angles, okay, so like that's where we were here. We had a choice of either alpha or beta. What you want to do is find the smaller angle. So with the law of sines, when you have a choice, find the smaller of the angles. If you do that, you don't have to worry about the or. Okay. In this situation, inverse sine will give you the correct angle. So I'm all about doing a minimum amount of work. I'm also all about getting things right. So this is what I do. If I'm given a choice and I'm using the law of sines, then I find the smallest of the available angles. All right. So there's an example of your side angle side. And just realize what we did. We found the third side, because that's what the law of cosines pushes us towards. Then we found an angle. Go for the smaller one, use the law of sines. And then once you got that second angle, the third angle basically comes for free. All right, so there's your side angle side. So I think we're going to take a break. Let me go ahead and pause the video real quick. All right, so now let's look at side, side, side. All right, that's the one case we haven't seen yet, but we're going to see that it's pretty straightforward. We know exactly what to do. Before we dive into that, though, real quick, let's do word of the day. So the word of today is scissors. I don't think we've used scissors yet. So again, because I happen to have them handy. Oh, no, we have. Did we really? That's funny. I don't have it written down. Must have been some time that I don't remember. All right, well then fine. We won't use scissors. How about we use glue? We use glue for word of the day. All right, so word of today is glue. So I'll go ahead and write that down. All right, so word of today is glue. Oh, did we use scissors last time? Yeah, it doesn't matter. Anyway, all right. So let's get to side, side, side. So I've got one up on the board. So let me go ahead and switch our view. All right. So here's an example of side, side, side. So I just gave you three sides. All right. So we got lengths of 16.2, 14.9, and 22.5. All right, so we know A, B, and C, and of course what we're looking for are alpha, beta, and gamma. So in order to find one of the angles, we're going to have to use the law of cosines. So the question is, which one? I mean, they're all the same. They all involve A, B, and C. It's just a question of, do we want to find alpha, beta, or gamma? Okay, well, there is one that I recommend that we find. And this is actually going to be gamma. All right, so what we're going to do is we're going to find gamma. So remember how with law of sines, there's sort of a good rule which one to find if given a choice? Same thing with cosines. If you have a choice, when using the law of cosines, find the biggest angle. All right, so why? Why do this? Well, the reason that this is advantageous is that when you do the law of cosines finding an angle, you use inverse cosine. And inverse cosine always gives you an angle between 0 and 180 degrees. The or is too big to fit in a triangle, so you don't actually have to worry about the or ever. So whatever the law of cosines gives you is the angle. So if we go for the biggest one, then we know that subsequent angles, if we use the law of sines, for example, we're guaranteed not to be in the or situation. Okay, so just a good way of going about this. If you're doing the law of sines, find smallest. If you're doing the law of cosines, find the biggest. All right, so I'm going to find the biggest angle. And which angle is biggest here? Alpha, beta, or gamma? All right, so I get a couple of people putting in gamma. Good. We know gamma is largest because it's opposite the longest side. All right, so we're going to go to the law of law of cosines that involves gamma. So that was the third one in our list. So that was the c squared equals a squared plus b squared minus 2ab cosine of gamma. And so what I'm going to do is I'm going to solve this for cosine of gamma. I'm just going to do a little bit of algebra real quick. So I'll swap the c squared and the piece with the gamma, with the cosine. And then I'll divide by the 2ab. So cosine of gamma is equal to this. All right, so now I'm ready to plug in my numbers. So we're going to get that the cosine of gamma here is equal to 16.2 squared plus 14.9 squared minus 22.5 squared over 2 times 16.2 times 14.9. And so this is just a calculator exercise. Punch this into your calculator, see what you get. And when you do the inverse cosine, you get 92.6. So I'm going to go and put this up here. 92.6 degrees. But there is no or. The or, it would actually be 360 minus that, which is way too big to fit in a triangle. All right, well, notice that it's also obtuse, which means none of the other two are going to be obtuse, which means we're good for the law of sines. Okay, so pick one of the angles, preferably the largest, and use the law of cosines to find that angle. But now that we've got gamma, we have a side angle pair. We've got C and gamma. So that means we can go and find the angles, or one of the angles, using the law of sines. So just to be good and keep up our practice with this, I'm actually going to find beta, because it's the smallest remaining angle. I mean, I already know I'm good. I know I don't have to worry about the or anymore, but I just like to get in the habit of doing it this way. So we're going to have sine of beta over b is going to equal the sine of gamma, so that's the one we just found, divided by c. So again, another calculator exercise. And what we end up with here is that beta is equal to 41.4 degrees. Now, we know that technically with the law of sines, we got to worry about the or, but we already know that that or is going to be way too big. It's going to be around 139 degrees, which won't fit with the one we already found. Plus, we knew that this had to be the smallest because it was the smallest side. All right, well, then alpha, of course, we're going to take 180 minus those two, and we end up with alpha being 46 degrees. All right, so there you go. So with side, it's pretty straightforward. Find the biggest angle using the law of cosines, then find the smallest angle using the law of sines, and then finally, the third angle just kind of comes for free. Okay, so this is actually kind of nice about inverse cosine, is that you don't have to worry about the fact that there's the or. You can just take it for what it is. So another option here would have been just to find all three angles using the law of cosines. Most people just don't like doing that because it's a little bit more complicated of a form. So if you decide to go back to the law of sines, best to do the biggest angle of the law of cosine. All right, now one other thing I do want to mention, we are doing an inverse cosine, right? Like in this, if I had left the letters, we had the gamma was equal to inverse cosine of what was it, a squared plus b squared minus c squared over 2ab, right? And there are going to be circumstances where we have to worry about the number in here being between plus and minus 1, right? So this right here, whatever that equals, this must be between plus and minus 1. Same reason with sine, inverse sine, right? Inverse cosine, only values that come out of cosine are between plus and minus 1. And so if that number is ever bigger than 1 or smaller than -1, we actually have a problem. And what that problem is in this case is that that triangle doesn't exist. Okay, so this might feel a little bit weird because you said, well, because I said, right, here's for something that you would say to yourself. Hey, Bruce, you just said side, we're guaranteed to find a solution. It's one of the congruence classes, everything's good. But it turns out that it is possible to have 3 side lengths that won't make a triangle. Right? An example would be like 1, 1, and 5. Good luck making a triangle with sides of length 1, 1, and 5. They're just not long enough to make it happen. And that sort of thing would cause this inverse cosine to have a problem. So I want to share with you just one more thing that is true about triangles, and it's something that you can use to help you with the sides to see whether or not it actually exists, or that combination leads to a triangle, I should say. And this is what we call the triangle inequality. You will see this again in calculus. It's kind of a thing. But the triangle inequality, basically what it says is that the sum of two sides, I put here any two sides, must be greater than the third side, or the other side. So in a triangle, you take two sides and add the lengths. It's always got to be more than the other side. And here's kind of the idea. Let's try forming a triangle by starting with one side that we'll have fixed, and then the other side will have lengths of random sizes. And basically what we can do to make this triangle is just sort of sweep these edges until they meet. But you can see that if the sum of those two lengths isn't at least the length of the third side, there's no way we're going to be able to build a triangle. Right? So if we make a triangle, no matter what, you'll notice here A plus B is longer than C. B plus C is bigger than A. C plus A is bigger than B. And that's what this says right here. So if you're ever in that situation where this isn't the case, then no triangle will exist, and you will see that when you try to calculate it. If you just dive to the law of cosines, you will see that you do not get a value. All right, but there you go. There's law of cosines. Yay. But you now have enough information or enough tools to solve any triangle. So I guess if we went historically, we just covered trigonometry in 2 days. And yet somehow we end up making an entire quarter-long class. But that's because there's a lot more to this than just measuring triangles. All right, well, speaking of measuring triangles, there is another thing that I want to talk about, and I mentioned this earlier. I want to look at area, because area of triangle, that's another measurement, and that's another thing that can be useful from time to time. So let's just put up here, area. So I'm just curious, as most people do. Do you guys know a formula for the area of a triangle? Something that you remember from once upon a time? Okay, so get a couple of people here telling me 1/2 base times height. Okay, great. It's exactly what I wanted to hear. A lot of you guys remember this, that there is a formula for area that's given by 1/2 base times height. And so in this triangle, the height would have to be some perpendicular, kind of like we drew when we developed both the law of sines and cosines. And then the base, of course, would be this length right there. And so it is 1/2 the base times height, because base times height would give you a rectangle. And if we were to make this a rectangle, you can see that these little triangles get duplicated. So that's why we have to cut it in half. So this is a formula most of us learn pretty early on for area of a triangle. It's good old 1/2 base times height. But the problem with this is you need to be able to know what h is. You have to be able to calculate that. And we don't always know that, right? Like think about the example I just showed you, where I gave you sides A, B, and C. If I'd asked you to find the area, that would have required you to go ahead and figure out this h, which is not easy. So let me show you a couple of other formulas for areas And these can be a little bit easier. They can be a little bit more direct when you're given certain information. Okay, well, here's what I'm going to do. I'm going to get rid of this h. And I'm going to get rid of this h by labeling these guys right here. So let's call this side A and call this side theta. I know normally I would use a gamma. I just want to use a theta because it's a little bit more common to see the formula with the theta. All right, well, look at the relationship between theta, h, and a. We know that the sine of theta is equal to h over a. So h is equal to a times the sine of theta. So I'm going to fire that in here. So another form for the area of a triangle is actually equal to 1/2 a times b times the sine of theta. So again, notice what these are. A and b are just a pair of sides, and theta is the angle in between them. Okay, so this is the form you're going to use if you know two sides and the angle in between them. This is also known as angle side angle. Or, sorry, side angle side. Two sides and an angle. So if you're in the side angle side case, this is a real quick way to get the area of the triangle. And it's terribly easy. It's just a matter of punching in the numbers and getting what you get. Okay, so get to know this formula. It's really, really useful. And it's another one that you will see later in calculus. All right, well, I would argue that this blue one is better than the green one because this second one, the one we just built, is really just given by angles and sides. But of course, there still is an issue, and that issue is that you need to know one of the angles. Well, it turns out that there's also a way to solve this, find this area, if you know just the three sides. Okay, so I'm going to give you one more formula here. Start it down at the bottom. Okay, this one's going to be A equals. And this is what this one looks like. I'm going to have to explain something, so just sort of go along for the ride right now. It's going to be the square root of s times s minus a times s minus b times s minus c. Okay, so clearly A, B, and C, those are the three sides. But the question is probably, well, what the hell is this S? Well, S is the semi-perimeter. So it's actually half of the perimeter. So if you take those three sides, A, B, and C, and add them up, and then divide by 2, that is your S. All right, so this one's kind of weird looking, no doubt about it, but it's really, really useful when all you know are the lengths of the sides. Now, I'm not going to prove this one for you. If you'd like to see the proof, come find me in an office hour. I'll show you, kind of work through it for you. But this one has a name. It's actually called Heron's formula. Named after the Greek mathematician that found it. He's sometimes also called Heron. I like to call him Hero because He's a mathematical hero. The hero's formula, Heron's formula. So it's almost magical that it works, but if you look at the geometry, it totally does. So let me show you an example of using Hero's formula. So I'm going to give you a triangle whose sides we know. And let's make it nice and easy. We have side lengths 2, 3, and 4. So we know that this does give us a triangle. If you look at any pair of these and add them up, it's bigger than the other one, right? 2 plus 3 is more than 4. 3 plus 4 is more than 2. 4 plus 2 is more than 3. So we do know that this is a legitimate triangle, but I want to know its area. So you can see how that first rule that you guys learned, that first formula, 1/2 base times height, is not very useful here. Because we'd have to specify one of the sides is a base. Maybe we'd go with this 4 because it's already oriented the way we like to have a base. But we'd still have to be able to draw on this perpendicular, figure out its length. And that's not an easy thing to do. If you look at the second one, the knowing two sides and an angle in between them, that would require us to find an angle here. Now that's doable. It's not terrible, but it would require us to use the law of cosines. I would rather not. So instead, let's use Hero's formula. Okay, so here's how this works. We got to start by finding S, the semi-perimeter. So we're just going to add up the 3 sides and then divide by 2. Take 2 plus 3 plus 4, cut it in half, which is 9/2 or 4.5. So we use the letter S again because it's the semi-perimeter. It's half. Okay, well, now let's just plug this, in addition to A, B, and C, into Hero's formula. So we're going to get A is equal to the square root of 4.5 times, which one's A, which one's B, and which one's C? So Erez just said doesn't matter. Okay, and that's actually the right answer. It doesn't matter at all, since we're going to subtract each one of them from S. Just subtract each one of them from S. So we're going to have 4.5 minus 2. That's 2.5. Now we have 4.5 minus 3. That's 1.5. And 4.5 minus 4 is 0.5. So it totally doesn't matter because of the commutative property of multiplication. So just do it however you need. So basically what I do, I take that S and then I legit just subtract each one and put those numbers in. All right, well, again, using our calculator, we get around 2.9. Obviously, we should have units on these, so to be good, let's say those are all meters. So this is 2.9 square meters, or 2.9 square feet, or square inches, or square miles, or square whatever the hell we have. Okay, so Hero's formula is super fast, super useful, especially when you're just given those 3 sides. That way you don't have to go back and try to figure out H or an angle or anything else like that. Again, be a good mathematician. Be lazy. Don't do extra work. Right? We've got a tool. Let's use that tool instead of doing more work. All right. So there you go. A couple of alternative ways of finding area. All right. So now you've done classical trigonometry. Classical trigonometry is measure angles or measure triangles, right? Find the lengths of sides, find the sizes of the angles and the areas. So I was kind of joking, but not really, that we did old school trig, like 2,000 years ago trig, in a day or two. Obviously, we're standing on the backs of lots of other people that have already done it before us, but classical trigonometry, now it's done. So this is the start, though, for us for applications, like real life situations, how we could actually determine things like heights of mountains and distances across rivers and things like that. So I want to share with you just a couple of examples before we call it a day of using trig. I'm not going to tell you whether we need law of sines or law of cosines or what have you. I'm just going to give you the scenario, and let's see if we can figure out what we're going to use in order to determine these things. Okay, so let's go to the board real quick. All right, so here's your first scenario. We've got a river, and we want to know the distance across the river. But the issue is there's no bridge. There isn't anything that we can actually use to get to the other side, so we don't have a boat or anything. But we've got the river. But the good thing about the river at this point is that it's fairly straight. But what we do have is on the other side, there's a tree. So we can see this tree over here on the other side. So we've got some surveying equipment. And so what we do is, standing on the shore over here, we're going to take a shot at that tree. And when I say take a shot, I mean we're just going to look at it through our device. And what we're able to do is actually measure the angle. We can measure the angle from the shoreline to that tree. So let's say that this is 17 degrees. All right. But then what we do is we walk to another point and do the same thing. And this time we measure an angle of 41 degrees. And along the way, we keep track of how far we went. And let's just say that we went 100 meters. Okay, so again, we're standing on the shoreline, we look over at the tree and we calculate an angle. Then we move down a little bit, do it again, and we get this information. Okay, so believe me, we now have enough information to figure out how far it is across the river. So this is what we're looking for, that guy X. All right, well, let's use our trig. Let's use what we know to figure out that distance. All right, so how are you going to do it? So Juan just says the law of sines. What does the law of sines allow us to do, Juan?
We should be able to get all three angles just by the given information, and then we'd have one of the ratios.
Okay, and you're right. With this triangle, this brown triangle, we definitely have enough that we can use the law of sines. But unfortunately, that doesn't actually include the side that we're curious about. Right, this length this length across the river isn't in that triangle, but you are right that we can solve everything in that brown triangle. And it turns out we do want to do that. We're going to use information from this brown triangle. But let me draw in this distance across the river. I'm just going to draw it over here so that it's part of a triangle.
Bruce, I'm not sure if it's the point of the problem, but yeah, why wouldn't you just take your measurement from that point in the first place and make it a 90-degree angle? Wouldn't that be a lot easier? And then you just kind of can work from there.
Well, all I can measure is an angle. I can't measure how far that is.
Well, yeah, but then you would know the 3 angles. I just figured it'd be easier that way. And then you can figure out what the hypotenuse is, and then you could just use the Pythagorean to find that distance.
Okay, so like if you were really doing this, yeah, if you could figure out exactly that point where you're perpendicular,
Yeah.
you could save yourself some time.
Isn't that how, wouldn't you be able to do that if you're using some kind of angle measurement device in the first place? That's why I didn't mean to.
No. Because here's how I want to go. Is it possible? Yes. And theoretically, everything's great. Application, it's extremely difficult. Even if you have something that's going to measure angles, so you stand at this spot, you shoot your angle over, the likelihood that you're at 90 degrees is very low, right? So you might go, well, I'm close. Let me move to another spot. Well, as soon as that happens, you're exactly here. We took our shot. Oh, it didn't work. We moved to another spot, right? So yes, if you by chance could get to the one place where you are directly across the river, use that as your starting point and then walk off to another location, yes, it would be faster and you could just use a right triangle. But I challenge you, and it's not just you, I would challenge anyone, even someone who's a seasoned pro with this kind of surveying equipment, to get the point that's exactly directly across. It's virtually impossible. So that's the difference between the real world and the math theoretical world. But your point is definitely taken, that if we could know that spot, then it would simplify this problem greatly. The problem is you can't always do that.
Right. I guess the best thing also would be to just take multiple angles to get like averages. Yeah. All right.
Yeah,
Thanks.
and clearly this is a simplified view because we're just using it as an example in trig. But everything that a surveyor would do in this situation would be based on this. And I think you're right. They would probably do it multiple times, try to get a better approximation. All right, well, here's what I'm going to do. I definitely like the idea of using the law of sines in here. And I'm going to find one of the brown lengths that I don't know. All right, which one? I don't really care. So let's draw that brown triangle again down here. And let's just talk about what might be easiest to find. So I know it doesn't quite look exactly the same, but close enough. So here's 17 degrees. There's our 100 meters. So can you give me another angle in here? Because one of the other angles should be pretty easy to get. So Kiva, you just said 139. And I'm going to guess, since that is the number that I want, that you saw which one this was. That's this guy right here, 139. And you find that by doing 180 minus the 41, because we know that it's a straight angle here. So that's 180 degrees, and we subtract our 41. Which means then we can find the other angle as well. And Kiva's already anticipating my question because she already put up in the chat 24. So we now have all three angles. We also have a side. which means we can use the law of sines. Okay, so it doesn't really matter which one I find. So I'm going to find this one. Let's call it C. So I'm going to have C over the sine of 139. That's going to equal 100 over the sine of 24. So I'm using my side angle pair to find this other side somewhere in that triangle. Okay, so we'll get to the calculator here in a second, but it's going to be 100 sine of 139 over the sine of 24. All right, so why I wanted that is, think about this big triangle. Now this one is a right triangle, right? Because theoretically, I can put that point wherever I want. And if I want to find x, but I know c, I can just use one of the trig functions. And specifically, for that 17-degree angle, which is the one that I know in there, I know that its sine is equal to x over c. So x is going to be c times the sine of 17 degrees. So all I got to do is take this thing that I just found for c and multiply it by the sine of 17. All right, so here's what I'm actually going to put in my calculator. You notice I haven't calculated anything yet. And in general, I try really hard not to calculate anything until the very end. Because if I calculate a number along the way, I'm probably going to round it. And as soon as I round it, I'm going to introduce more possibility for error later. So I just try to bang it all out at once. All right, so let's see what this gives us. So we'll do 100 sine of 139 times the sine of 17 divided by the sine of 24. All right, my calculator gives me 47.16. So we know that this river at this point is a little bit more than 47 meters wide, which is going to be way too long for us to try to measure with like a string or something. Because I know other people, sometimes people are like, well, why don't you just throw a rope over, try to get it like attached and then, you know, measure where it is on the rope. Yeah, good luck throwing it 47 meters. That's longer than a football field. Most people aren't that strong. Anyway, so here is an application, a legit, real application. Probably not for finding the width of a river, but this is the sort of thing that's done in order to find like the height of a mountain, heights of trees, and so on. All right, well, I said I was going to do a couple of examples, but that pretty much filled our time. So I'm going to go ahead and stop the recording here. But actually, before I do that, let me just remind you about where we're going and what's going on. So we have our next exam a week from today. All right, so I think we're not going to do a quiz on Wednesday, but also just to prepare you for this exam, expect it to be basically on identities and equations. So I think that was chapter 8, maybe chapter 9, I don't remember what the number was. And then it will also include laws of sines and cosines, and so solving these triangles. So you'll be happy that that part's on the exam. It'll be a nice break from identities. Anyway, okay, so that's a week from today. That'll be our last regular exam, but we'll talk more about that on Wednesday. All right, so let me pause the recording.